So taking a look at this, kind of taking that free energy diagrams, Gibbs free energy, talking about this. So what is delta S, or delta H is just the change in enthalpy. All right, this is a change in enthalpy. Enthalpy. Don't worry about spelling it right. P. This is the change in entropy. So enthalpy is potential energy. Entropy is disorder. Which one usually matters more? It's usually delta H. Matters more in these equations. That usually has a bigger factor. If something is exothermic, what kind of delta G does it have? So delta H and delta G, sometimes we get these mixed around. Delta G is Gibbs free energy. It takes into account entropy, but the same kind of rules apply. So this would have a negative sign when it's exothermic. It has a positive sign when it's endothermic. How can you estimate delta H? Don't overthink this. It's just all about bond association energies, right? What bonds are formed, what bonds are broken, right? And the way you do it is you take bond association energy, so BDE. So really it's just bonds broken, and you can look those numbers up, minus bonds formed. And if the bonds that you formed are more stable or higher in higher in energy, then it's an exothermic process. So that's all we're looking for there. Why does it matter? That's maybe the most important question. Why does this matter? Right? It helps us predict reactions. Right? We're trying to predict reactions. We think about reactive bonds and unreactive bonds. Polar bonds have lower bond association energies. They're easier to break. So this is just kind of playing into that stuff we've already been talking about electronegativity, size, and all those kind of things. Right? How about labeling the diagram? So labeling stuff. Let's get ready to label stuff. So 1 is the reactants, or I always call them starting materials. What's 2? 2 is an intermediate. Remember, intermediates you can actually isolate. What about 3? 3 is the products. And then 4 is a transition state. This, instead of being activation energy, this is actually delta G. And have you heard double dagger? Have you heard that before? Like, what does that mean? It's just a fancy way of saying transition states. Transition states, that's what the double dagger means. So it's the activation energy to go from there to there. And then this one is just delta G. Again, this is thinking about thermodynamic products. The height of the hill is thinking about kinetic products. So now the second part of this, we're going to talk about kinetics and thermodynamics and how do we actually look at them. So one of the first things people need to think about, like, how do we actually calculate a rate of reaction? So when I think of rates of reaction, I think of fishing. So here we go. So if you're this guy, this person, the fishing pole, and here's a pond. I'm terrible at drawing, but hear me out. All right? If this person is fishing and they have a hook, if there's more fish in this pond, the more likely, right, this person is going to catch fish, correct? And how does that relate to this? Well, concentration matters, right? Concentration. How much you have of either thing will affect the rate, right? If you have two things that need to run into each other, the more of them you have, the more likely they'll run into each other, right? This is the honey hole. This is the honey hole, right? So these fish are rolling around in here, and you have a bobber. Who's ever gone fishing and had the bobber go down, but then they start reeling fish in, and then they don't have any fish? Who's ever done that? Yes, right? What happened? Obviously, the fish ran into your hook, right? So it had enough energy, right? So it had enough energy to do it, which is great, but you didn't catch the fish. Why didn't you catch the fish? Because the orientation was wrong. Right? The orientation was wrong. You didn't hook the fish. So what do you need? You need lots of reactants, A and B. You need them running around. You need to have a lot of energy. They need to hit each other. But they can't just willy-nilly hit each other. They need to hit each other in the right way. Right? We talk about an SN2 reaction. Right? These things have to find the antibonding orbital. Right? They have to find each other, not just hitting each other, but hitting each other in the right way so they can actually react. So concentration matters, energy matters, but also really orientation matters a lot too. Go through the second part together. So in this case, I want you to circle the kinetic product. So the kinetic product is going to come from which pathway? It's going to come from the pathway with the lowest activation energy, right? Because kinetics talks about activation energy. So that would be product 2. And in this case, product 1 activation energy is actually higher, greater than the activation energy for product 2. Delta G double dagger. Do we see that? So now we're thinking about thermodynamics. So now we're not worrying about the activation energies. All we're looking at now is the energy difference of these products. So which one's the thermodynamic product? It's just the one with the lowest energy, right? So that would be product 2. So in this case, the delta G of product 1 is less than the delta G of product 2. Right, it's a more stable product. This is all thermodynamics is thinking about. So there's 2 examples here.